But I would just like to introduce our next speaker, who I believe is with us. So I really have a pleasure to introduce Professor Yong-Lae Park, who is from the Department of Mechanical and Aerospace University at Seoul National University. So Professor Park works in the domain of soft robotics, wearable robotics, medical and bio-inspired systems. He's won many Best Paper Awards and Career Awards, and has also made significant advances towards our understanding of soft sensing. So I think following up on the plenary talk we had this morning, focusing on manipulation and tactile sensing, this brings in some really interesting additional insights. So thank you very much, Professor Park, for joining us, and I will hand over to you to start your talk.
Okay, thank you very much for the introduction. So I can start my talk. So hello, everybody. Yeah, thank you very much for inviting me to this exciting event. And my name is Yong-Lae Park, as Josie introduced. I'm a professor at Seoul National University. Today, I'm going to talk about highly stretchable robotics kit using liquid embedded elastomer. The key material we've been using for our soft sensor is eutectic gallium indium, which is a liquid metal at room temperature. The idea of making soft sensors is really simple. You first make an elastomer layer with embedded microchannels. By injecting liquid metal into the microchannels, you can make a flexible and stretchable circuit. This is a triple layered sensor for multi-modal sensing. Okay. So then if you compress or stretch it, the resistance of the microchannels change and you can detect the deformation. So as you can see in the video, you can detect multi-axis strains and normal pressure in real time. So by having the calibration result, you know the sensor can recognize which direction you are stretching and how much you are stretching, and also the sensor detects the direction of the strain, and also you can make a compression and it can detect the compression. Then where can we use these sensors? One immediate application would be direct integration with the soft actuators, like proprioceptors in biological muscles. There have been various types of pneumatic artificial muscles made of polymer materials, but it is not easy to equip them with conventional sensors due to their high stretchability in the structure. So by embedding our liquid metal sensors to soft artificial muscles, we were able to directly control both the force and the position of the actuator individually, as you can see in the plus in the slide. Okay. Another application would be force sensing in a miniaturized device. This is a prototype of catheter for cardiac ablation. At the tip of the catheter, we were able to embed a liquid metal sensor which detects tip contact force. So we were able to do dynamic force control of using the soft actuator unit at the end of the catheter. So here the diameter of the catheter prototype we built were around 1.5 millimeters. So in a really, really small size device, we were also able to embed these liquid metal sensors. So far this is component level, but if we extend this to system level, we can first use these sensors for a wearable sensing suit. So the left figure shows a wearable sensing suit for detecting lower body motions, and the right one is a whole body sensing suit. Although the human body is covered by three-dimensional complex surfaces, the sensors were able to easily conform to the body and provide information on the 3D motions. So as you can see in the video, we have 6 sensors on the lower body, 3 sensors in each leg, and then we were able to detect running or walking motions using this sensor suit. And also, if you extend the number of sensors, you can make a whole body sensing suit. So here we have 20 sensors around your body, and then we were able to detect 3-dimensional motions of your body like this. So the top figure shows the ground truth, and the bottom figure shows the prediction, and the right figure shows the comparison of the two signals. Okay, so another application is robotic skin for improved human-robot interaction. This is a robotic arm with inflatable skin for increased safety and human operators. We embedded our software sensors in the skin, and the robot was able to physically interact with humans. As you can see in the video, the robot is equipped with these inflatable skins, so it can be easily interacting with human operators, and it can be also safe to human operator. So if you touch this skin, the embedded software sensor detects the touch, and then the robot can be interactive with human intention. Okay, so we have been building these sensors, and it is quite exciting to see all different applications. But during the development, we had several questions for further improvement, as you can see in the slide. So I'm going to use the rest of my time to answer these questions. The first question is, can we reduce the number of wires? If you want to increase the spatial resolution or the sensing area, you need to increase the number of sensors. But it will also increase the number of signal wires, which is a headache in terms of fabrication and robustness. So one idea we had to solve this problem is processing the sensor signal in a frequency domain. Since the liquid metal channels can be considered as a variable resistor, by adding a capacitor and an inductor, you can simply construct an RLC circuit. And each circuit can be used as a bandpass filter. So as you can see in the bottom figure, as the number of sensors increases, the number of wires also increases for different methods. But theoretically, our method uses only 2 wires, regardless of the number of wires. So this is the actual prototype, and each liquid metal channel has its own capacitor and inductor, and which enable the detection of multi-touch sensing as well as a single touch sensing. So as an application, we built different systems. The first application is a fingertip sensor. So in this sensor, 9 sensors were embedded, but only 2 wires are required to detect all the touch signals from the 9 sensors. And then while doing manipulation job, you can detect the activities on your fingers. We can also make insole sensors. So in this sensor, we also have 9 sensors. And then you have only 2 wires coming out of the shoe. So even though there are some commercial sensors, they can detect your foot pressure distribution. So those are expensive and they require a lot of wires. So in this application, we were able to build software sensors using only 2 signal wires, but with high density sensors. Okay, let's move to the next question, which is, can we automate the fabrication process? The injection method you're looking at in the video is great, but it's a manual process and it caused a lot of problems in fabrication. So we wanted to automate the system, and we constructed this system. The system has a motorized XYZ table and pneumatic dispenser. And using this system and by optimizing the parameters, we were able to draw a liquid metal trace as thin as 25 micron. And then, as you can see in the figures, we were able to draw these liquid metal patterns on an angled surface or curved surface, and really, really small sensors we were able to make. And since we have laser sensors, distance sensors, we will also draw these liquid metal patterns on an arbitrary 3-dimensional surfaces like this. Another manufacturing method we were looking at is by thin film coating, which is used semiconductor fabrication area. So in this method, we use the thermal evaporation, and we deposit very thin layers of indium and gallium multiple times. But once you deposit these multiple layers of galliums, because of the oxide skin, they are not really conductive. But if you make a stretch for the first time, the oxide skin breaks, and then there are leakages of liquid metal coming out, and then they construct 3-dimensional microstructures and micro network, conductive network. So as you can see in the figures in the plot, the first stretch makes the connection, but after that, you have a really nice response of the resistance. And you can build very, very thin sensors using this method. As you can see here, we were able to deposit a liquid metal layer as thin as 1 micron, And also the layer was about just 5 micron or 10 micron. So in the video, we can see this is highly robust, and we can build a skin mountable device. And also we can use this sensor as a teleoperation system. Okay, so the next question is, are there any alternatives to liquid metal? So the answer is yes. And then we use the ionic liquid, which is similar to saline solution for motion sensing glove. And also we were able to build a system that can draw this even ionic liquid patterns on an elastomer surface. Okay, so now let's move to the last question, which is, can we realize multimodality and multifunctionality in a simple structure? So if we want to have multimodal sensors or multifunctional sensors, you need to add more elements. That makes the structure complicated and also fabrication difficult. So we had an idea of combining heterogeneous sensing mechanisms in a simple single structure. In this structure, we have a microchannel filled with the ionic liquid, which is transparent. But by adding LED and photodiode, you can use this structure as an optical waveguide and also resistive sensing. And by adding conductive fabric outside of the body, you can have another modality. So by monitoring the sensor signals from all these different sensing mechanisms, you can decouple different deformation modes. So as you can see here, you can stretch, bend, and then you can also stretch, and then you can compress. And you can use this as a new types of human-machine interface. Okay, so because of the time, I think I have to stop here. And we try to answer more and more questions for further development and applications of these software sensors. Yeah, thank you very much for listening. And I will be happy to answer any questions at the panel discussion.